Hi everyone, welcome to the lecture 18 of this Classical Mechanics 1. So in this lecture 18, we'll discuss about symmetries and conservation laws. Okay. So in this lecture we will discuss various symmetries, and for each symmetry we will see there will be some conservation. So we will discuss in general symmetries and conservation law. Before that, let me recap about the previous lectures. So in last lecture, last class was a tutorial class, and towards the end we had to hurry because of time. Let me recap that problem. So we were discussing two problems. One was that the pendulum with the spring, not with the string. So pendulum, simple pendulum, but the string is replaced by spring. So that case we said that this length will change, but at any moment of time it will preserve the constraint that if the coordinate is x and y for this pendulum, then x square plus y square will be the L square. So this is a kind of time dependent constraint, but we will have degrees of freedom even for this system will be 1, and we have found the Lagrangian. Similarly, so I was in hurry, so probably you people missed this point, and so this was a dynamic constant because it's depend on time. Length is not fixed all time. Similarly, the other problem we discussed that two simple pendulum, and these two pendulum is connected by a spring of spring constant. Here also that total degrees of freedom will be this pendulum are supposed to be in a plane. So total degrees of freedom supposed to be 2 plus 2 for both pendulums, but there will be 2 constraint because of the length of the string. So total degrees of freedom even for this system will be 2, and we have constructed the Lagrangian. So this point should be clear in your mind. So far we have learned that how to construct. So in last few classes we have paid attention to construct the Lagrangian. So we know how to construct Lagrangian. So how to construct, find equation of motion, Euler Lagrange equation of motion. Then you should able to find, these are generally second order differential equation, and one can find the solution of this equation to find the solution of the classical system. So you should practice with many different problems, whatever you have studied in your high school, the previous semesters, that you should practice those problems by constructing Lagrangian now. So you should able to construct Lagrangian and then find equation of motion. Okay. So this is the recapitulation of last lecture, which was a tutorial class. Now today we will discuss symmetries and conservation laws. So this is the topic for next few lectures. So symmetries are very important in studying physics. That we have seen in many places that symmetries, by symmetry will mean here, by symmetry will mean that our theory will remain unchanged. Under under certain transformation. So, we know various transformation in physics. For example, we know the translation of coordinates. So, example of transformation coordinate translation like Ri going to Ri plus A. This is also called the shift of coordinate, shift of origin. Similarly, we can have a time translation, rotation is also a transformation, rotation of coordinate axis is also symmetry. There are many type of transformation, and symmetry, when we will call symmetry, if your Lagrangian, or more generally if the action of the theory is invariant under this transformation, motion, then we call that transformation a symmetry. For example, if suppose my Lagrangian, Lagrangian is invariant, or it changes by like this, or changes by c time this, or L plus df dt c. And all these three cases, you will find that your action will be same, or maybe delta s will be delta s prime. So, all these cases you will find, if you have under certain transformation this holds, then we will call that transformation is a symmetry of the theory. Then that particular transformation is symmetry of the theory. Okay. So, we will discuss several symmetry, and we will see what will be their consequences. So, this is the idea, and if it is a symmetry, then dynamics of the system will be the same. Same even after applying this transformation. So, let us consider few symmetry. First, we will consider homogeneity of space. First symmetry we will consider homogeneity of space. A space is called homogeneous if the theory remains unchanged under space translation. We already defined the space translation Ri for each coordinates. Ri prime will go to Ri plus some constant c. So, if this is also called translation in space. Epsilon we consider is a constant, is constant vector, because Ri is a vector. So, it also has to be a vector. So, under this transformation, if Lagrangian remains invariant, then of course action will remain invariant. So, if the Lagrangian remain invariant, then what will get that what kind of conservation will get, that we are going to find. So, what I said, that whenever there is a symmetry, it will have some consequences. So, that we are going to check. So, we will consider few symmetries and their consequence I will check. I will teach how what quantities will be conserved. Now, we will see under this. So, if I change r to r prime, so let us consider my Lagrangian is ri dot, and we are checking that under this transformation how it change. So, Lagrangian will change. So, let us change of Lagrangian will be delta L delta Ri, and there are many Ri. So, I will sum over this dot delta Ri, because this is a vector. So, I am using dot, plus sum over I delta L delta Ri dot, this is a vector dot with delta Ri dot. Okay. We will have this formula because of the chain rule of differentiation. Lagrangian is function of Ri's and Ri dots. So, we will have the chain rule of differentiation. To obtain this formula. Now, from this transformation, it is obvious that delta Ri is epsilon I and delta Ri dot is 0, because epsilon I is a constant vector. This is a constant vector, as I mentioned this. So, if I substitute this in my equation, delta L will get delta L equal to sum over I delta L delta Ri dotted with epsilon I, because delta Ri is your epsilon I and delta Ri dot equal to 0. Okay. Now, I will use Euler-Lagrangian equation. So, recall Euler-Lagrange equations, Euler-Lagrange equation, that ddt of del L del Ri dot is minus del L del Ri equal to 0. So, I can substitute this delta Ri by this in the above expression. So, using that we will get delta L will be the variation of the Lagrangian will be sum over I ddt of del L del Ri, okay, dotted with epsilon I. Okay. But by our definition of momenta conjugate, delta L delta Ri dot is by definition is the momentum conjugate to Ri. So, let us denote with the Pi. So, this expression is then sum over I ddt of Pi dot epsilon. So, this we can write as sum over I epsilon I dot Pi ddt of Pi dt, and we will write since epsilon is constant, we can write this ddt of sum over Ai dot Pi. Okay. And this implies that if you consider that all okay, so this incident that if you consider sum over all I is Pi, so this will lead to dP dt will be equal to 0. If delta L is 0 under the space translation, because we want that variation of Lagrangian is invariant. So, from there we find the total momentum of the system will be conserved. So, total linear momentum is conserved if the Lagrangian means invariant under space translation. Okay. Homogeneity of space implies the conservation of linear momentum. This is also related to the Lagrangian. This Lagrangian will be invariant under space translation when this del L del Ri should be 0. So, that we obtain. So, if del L del Ri is 0, then this the position coordinate is cyclic. So, we have also seen then for each cyclic coordinate the momentum conjugate to this will be conserved. So, we find that homogeneity of space, that is when you have a space translation, your like system dynamics remains invariant, then that leads to the conservation of linear momentum, and that is also related to that spatial coordinate is cyclic. Okay, so this can be understood with a simple example. So, let us consider a very simple example, and I want to illustrate that this result holds even partially. So, simple example, let us consider a two dimensional Lagrangian x dot, y dot, and x and y like this, half m x dot square plus y dot square minus say half k x square. Suppose this is your Lagrangian. Now, notice that this Lagrangian is not homogeneous along x direction, because if I make x going to x plus a, the Lagrangian will change. Okay. Similarly, but this Lagrangian is along y direction, as y going to y plus b will not affect the Lagrangian, because there is no y dependent. So, y is also cyclic. So, here immediately we can say that Py will be conserved, but P x will not be conserved. So, this conservation law is partially true. This concludes the discussion on that homogeneity of space and the conservation of linear momentum. Now, we will consider another symmetry, which is the homogeneity in time or time translation symmetry. So, next symmetry is time translation symmetry. Okay. So, time translation symmetry, if the system remains invariant, then we will call the system is homogeneous. So, if the system change, then we call so if the system remain unchanged under this time translation, then we call this time is homogeneous. In case of when we discuss the construction of Lagrangian for free particle, we have seen that space is homogeneous, time is also homogeneous for a free particle. The meaning of homogeneity there is that if you look at the system dynamics at 10 o'clock or if you look at 11 o'clock, you will have the same dynamics. Similarly, when for a free particle, I already mentioned the space is also homogeneous. So, when you look at the dynamics at some space, and it is in a different space, it will have the same dynamics. You will have move in a straight line without changing its direction. Okay. So, physically these are the meaning. So, for time translation, so if we substitute T prime is T plus A and the system dynamics remains invariant, then we call that system is time, for that system the time is homogeneous. So, let us consider the Lagrangian. Let us consider the Lagrangian is Q I and Q I dot. I am not writing its explicit dependent on time, because if there is explicit dependent on time, then it is not time translation. So, if it does not depend on time, then time is cyclic and the system remains invariant under time translation and it is homogeneous in time. So, let us calculate this quantity, try to find what will be the conserved quantity in this case. So, we will find dt dl of dt, total derivative of this Lagrangian with respect to time. So, let me write here, assuming no no explicit time dependence, because if there is explicit time dependence, then you will not have time translation invariant. Okay. So, now this again using the differentiation chain rule, I have to differentiate with respect to q I and then q I dot and sum over all I plus del L del q I dot will be del q I double dot. So, this will be the my dl dt. Okay. Okay. So, now if I use the Euler-Lagrangian equation for this part, we can write as sum over I ddt of del L del q I dot plus del L del q I dot q I double dot. Okay. Okay. This further I can write as sum over I ddt of del L del qi dot qi dot. So, first term, when I differentiate del L del qi dot, you will get the first term. So, and the second term will be that when I differentiate the second term. So, this can be written like this. Now, generally for conservative system, we find that kinetic energy system is generally a quadratic function of generalized velocity, and for conservative system del L del qi dot equal to 0. Okay. So, if your system is conservative and follow this rules, then I can write this expression can further be written equal to del L del qi dot t minus u qi dot. Okay. Now, this is sum over I d dt of del t del qi dot qi dot, because del u del qi dot equal to 0 I mentioned for conservative system. Now, because of time, I will stop here and we will continue the derivation of this in my next lecture. I will continue with this. Now, we will see from here that what quantity will be conserved if we have time translation invariant. So, if your time is homogeneous, what quantity will be conserved, that we will see in the next class. So, let me stop here. I will continue this derivation in the next class. Thank you.